Based on recent studies, buildings are responsible for about 35 to 40% of all energy used globally.
And as the awareness of the dangers of global warming grows, a huge amount of research has been performed to find methods that would result in minimizing the amount of air pollution and the energy consumption in buildings.
One of these areas of research is cooling. And recently developed approaches on this issue are focused on radiative cooling.
A technique requiring no energy to lower the ambient temperature, thus considered as a key to help to slow down the disastrous effect of global warming. In general, radiative cooling is the process by which a body loses temperature by thermal radiation. Now, what's a radiative cooler? A radiative cooler is a thin film that you apply to the body in which the temperature of the body will be lower than its ambient temperature.
To realize radiative cooling, two main concepts should be understood. First of all, and from a thermodynamics point of view, it is known that heat will spontaneously flow from a hot to a cold body. Therefore, heat from high temperature tertial bodies up to 300 kelvins can always flow towards a low temperature sink. In our case over here, it's outer space with a temperature of 3 kelvins. Secondly, there is a transparent window in the atmosphere, ranging from wavelengths of 8 to 13 micrometers, that could be used to exchange heat between Earth and outer space in the form of infrared radiation and not get trapped and reflected back to Earth. On these two concepts, radiative cooling is built. These films reflect radiations coming from the sun while having its emissions in the atmospheric window. An ideal radiative cooling would have 100% reflection over the whole solar spectrum while simultaneously having 100% thermal emission in atmospheric window.
When we move on to the big question, what materials could be used to achieve radiative cooling? We would start by base materials. Base materials are rare earth metals and are selective emitters because they have high absorption in the infrared region. The composition of these metals with ceramic materials like titanium is the perfect case. But the problem is that at high temperatures, emissions from other constituents dominate these metals. Examples of these metals would be like zinc sulfide or cadmium sulfide.
Since all materials mentioned above did not meet the standards required to make them perfect radiative coolers, this made the scientific community move to using metamaterials. In general, metamaterials are artificial structures which can realize various optical properties that do not exist in nature and have been developed with the advancement of high-level nanofabrication methods to create perfect absorbers, reflectors, and spectral filters. There are three methods in general to create metamaterials. The first one is using a film structure, moving on to nanostructures, and finally random particles. For film structures, film structures consist of layers that when put together will achieve the required optical properties to achieve radiative cooling. Here are some examples of film structures that achieve radiative cooling, and on this basis a group of researchers designed a film made up of multiple layers of silicon dioxide and titanium dioxide on an aluminum or silver layer, thereby consisting of low and high index materials to utilize their emission spectra and high absorption caused by the phonon polaritarian resonance. Using this simple, easy to manufacture layered film design, the ability to lower the temperature 5 Celsius below ambient temperature using a radiative cooler power of 100 watts per millisquared was demonstrated. The second way of designing these radiative cooling materials is using nanostructures. These nanostructures are made to select an absorption and emission spectra refractive index of a material with respect to a frequency that could be acquired. Here are some nano modifications that allowed scientific community to achieve the perfect radiative coolers, and a group of researchers used this space to build a silicon dioxide photonic crystal absorber which could be used as a radiative cooler. Silicon dioxide was chosen because it exhibits a strong phonon polaritarian resonance in the atmospheric window region. The absorber was a square lattice photonic crystal with periodicity of 6 micrometers, made up by etching 10 micrometers deep air holes into a double-sided 500 millimeter polished fused silica wafer. When placed under direct sunlight, this device managed to reduce the temperature by 13 Celsius from the ambient temperature. Finally, using random particles. The concept of random particles is very close to the concepts of nanostructures. However, this time the scientific community want to achieve a higher speed of manufacturing and decrease the cost required. Therefore, instead of arranging the nanospheres with a certain order, the scientific community chose to arrange the nanospheres randomly and in the same time achieve the required properties. One of the researches done on this area showed that by using densely packed titanium dioxide particles on top of densely packed silicon carbide or silicon dioxide particles, all in an aluminum substrate, can be used for radiative cooling purposes. This design was able to produce an 8 Celsius reduction below the ambient temperature in a region with high humidity like Qatar.
Moving on to paints and coatings, they also have high reflectivity and absorbivity. Now, like base materials, they aren't as efficient to the degree that makes their impact noticeable. A good example of these would be polycrystalline lead and sulfide onto polyethylene foils, as these semiconductors are expected to block solar radiations as being transparent in the atmospheric window in intrinsic and represent high reflectivity. To elaborate more on the uses of radiative cooling material in Qatar, my partner and I went to conduct an interview at the Lusail football field, which is the largest football field built for the 2022 Football World Cup. And we went to the cooling towers of that football field.
We interviewed a mechanical engineer over there, and he explained to us how cooling works, and we asked him our questions, and the answers was as follows. But I also want to ask, like, is this the only way of cooling? Do they consider the materials they build the stadium from? Like, do they consider certain materials?
Yes.
Like,
See,
to
make the proper cooling, to save the energy, there is many materials like concretes, you know. This concretes, it will like protect the sun heat to the building. Okay, there is many composition of concrete. This is dependent. This is related to all architecture and civil. Okay, means you will, okay, this SRG 30, this SRG 40, this is Portland cement. Okay, this Portland cement, if I'll apply on the wall, there will be a conductivity, heat transfer conductivity less.
Yes.
Okay. So you need less, no, heat transfer conductivity. K, you know, K. We study. Okay. Radiation. What you call radiation and these things. Okay. So from outside to inside, there will be a less radiation. Means instead of 10 BTU per hours, so by using Portland cement,
it's making your job easier.
Yeah, very easy. It will. But this thing somebody should think during, you know, like consultants. You know, normally consultants, they are thinking on this. Okay.
So like
even glasses, you want to put glasses. Okay, there is also type of glasses. But this glass
it
will
be
protect.
Like strong.
Yes.
And at the same time, it's not like the thermal.
Yes, thermal conductivity. Correct. I forget that one. Thermal conductivity. K. Okay. Yes. Thermal conductivity, less thermal conductivity. I mean, it will only like 2 BTU per hour it will pass instead of 20 BTU per hour. If you take normal window at our home, okay, you will, when in summertime you open, khalas, you need 2-3 ACs. Okay. Exactly. But in some green buildings, okay, when it comes to green buildings, what they will do, they will select the expensive one. Why? Because this expensive, this money, they can manage within next 10 years.
And it will save energy. Like,
yes, it will save energy.
In this amount
that is called green energy, no? Green building.
Green building.
So that what happening, they are putting glasses everywhere, and later on what they will do, they will save their lights also, daytimes.
As you heard in the video, radiative cooling materials could be used to decrease the amount of cooling power required in buildings in general and stadiums in specific.
And we hope this video will contribute to the starting of a lot of researches in the topic of radiative cooling material to reach the goal of Qatar's 2030 of a greener future.
And most importantly, we hope that this video made radiative cooling materials more familiar to you and in all aspects. Thanks.